us about magnetic fields. Let's welcome Alvina.
Okay, hi everyone. Thank you very much to the organizers for having me today. I'm Alvina and I'm one of the new NCTS postdocs. In fact, I just moved to Taiwan like 2 months ago. So today I will be telling you a little bit about our work on how to decode the invisible universe. And by invisible, I mean how do we see and measure magnetic fields with fast radio bursts. So this work is in close collaboration with Jennifer Chan, who gave a talk yesterday. And the reason why we want to learn more about magnetic fields is because we know that magnetic fields are everywhere around us, and yet we don't know two of the big questions. So first of all, where do magnetic fields come from? Where do the first magnetic fields come from? And how do they evolve with the structure formation of the universe? And here in the background are the beautiful northern lights, and there are beautiful evidence of the Earth's magnetic fields interacting with the charged particles carried by the solar wind. So if we move on to larger scales than the Sun and the Earth, the galaxy that we live in, the Milky Way, is also magnetized, as well as nearby galaxies and galaxy groups like the M51 and the Stefan's Quintet. Now, if we move on to much larger scales, like galaxy clusters and beyond, it becomes increasingly more difficult for us to see and measure magnetic fields because they are a lot weaker. And yet, it is important for us to correctly infer the magnetic field properties at such large scales, because they should hold some evidence of the first seed magnetic fields. So we still don't know for sure where the first magnetic fields come from, whether they're primordial in origin, meaning it's generated soon after the Big Bang, or maybe they are generated through some astrophysical processes after the first stars or the first galaxies form. So different seeding mechanisms may imprint different signatures in observations. But here what I'm showing you are two extreme scenarios from the ENSO simulations, and on the left is what you see in the primordial case, where a small seed field is planted at the start of the simulation and it's evolved as the universe expands. And on the right is the astrophysical case, where the magnetic fields are seeded much later on by stars and AGN. So the colors represent the average temperature and average magnetic field strength, and at first look, they look rather similar. So inside the densest knots are galaxy clusters and groups, and they reach similar levels of magnetization. So we're looking at about microgauss levels of magnetic field strength. However, as we move towards the outskirts of the clusters, you can see that the morphology starts to change. So in the primordial case, it looks more filamentary, whereas in the astrophysical case, it looks more blobby. So what does this mean in terms of magnetic field? So people can predict the rotation measure signal for the same set of simulations, and this is what we may expect to see. So here we can see that in the two cases, the magnetic field strength peak at similar levels, so at the green and yellow regions, which are about microgauss levels of rotation measure. So this is in rotation measure, so this is in radians per meter squared. So many thanks to Dan for giving a good background of rotation measures. I'll skip that and talk about rotation measures here. And you can see that in the primordial case, it looks more filamentary as well. In the astrophysical case, it's more blobby. And if I recall correctly, in the primordial case, the average rotation measure is about 1 to 10 radians per meter squared, whereas in the astrophysical case, it's much lesser than 1. So what this means is that there's a difference of an order of more than 10 outside of clusters. So unfortunately, this is not observable using present-day radio telescopes because of the sensitivity limit. However, it may be possible for us to do this with the next generation of radio telescopes, like the NGVLA, the SKA, FAST. I think the Chinese name is even more beautiful, Tianyan, which means like heaven's eye. And of course, burst. So these FAST and burst, while they are primarily dedicated to do FRB science, but we do expect that they will help us improve our understanding of radio polarization and hence magnetic fields, and also improve our understanding of the origins and evolution of large-scale fields. So I hope at this point this is why FRBs are promising candidates for cosmological probes because of their special property where we have extra information about the column density along the line of sight due to the dispersion measurement. And they may be able to probe to lower values of rotation measures compared to, say, radio galaxies. So our current status of what we know using FRBs is that magnetic field strength at such large scales could be about a few tenths of nanogauss and a correlation length of about tens to hundreds of kiloparsecs. So I hope at this point I've sort of convinced most of you, if not all of you, that it's therefore timely and important for us to better understand what this rotation measure method is. So by definition, the rotation measure tells us the amount of rotation when the polarization plane of light rotates in a magnetic field. So observationally, one can measure the rotation measure by measuring the polarization angles on the sky at different wavelengths squared. Theoretically, the rotation measure is actually a variable that is derived from the theory of polarized radiative transfer. So you may recall bits and pieces of this from Jennifer's talk yesterday. So this rotation measure tells us a little bit of information about the magnetic field strength along our line of sight, provided that there is no absorption, there's no emission, there's no Faraday conversion, and that only thermal electrons are present. So this is the equation that's widely used in literature. Most of you may be familiar with it. And it is often assumed that the correlations in the observed rotation measure fluctuations can be used to probe the length scales on which magnetic fields are changing. So the conventional approach is to model the rotation measure fluctuations as some kind of a random walk process, which means that the standard deviation of rotation measure can tell us a little bit about the magnetic field strength along the line of sight. And most studies on large-scale magnetic fields uses this expression here. So the question now is, when is it justified to be used and when does it deserve caution? So to address this question, we carried out Monte Carlo simulations to calculate the rotation measure fluctuations by building models of various magnetic field configurations and thermal electron number density distributions. And we compared the results from the conventional approach and the results from a standard polarized radiative transfer. So let's do an eye test. I'm sure most of us are quite tired from staring at the screen and sitting in this conference for a few days, but please entertain me and let me know if you can spot any difference between each panel that I'm showing on the screen here. So people online can join too. If you think there's no difference, please raise your hand. Okay, cool. So the good news is most of you have pretty good eyesight. So all of these panels actually look the same. But what if I tell you that these are actually rotation measure maps that are generated using completely different distributions of densities and magnetic field strengths? So in fact, what you see at the top panels here are rotation measure maps that are generated using densities and magnetic field strengths with a Gaussian distribution, whereas the ones at the bottom are actually generated from densities and magnetic field strengths with a uniform distribution. And I was being extra cheeky here, so I deliberately made the magnetic fields in the bottom panels unphysical, so they're actually not divergence free. So what this is trying to show us here is that it is actually not trivial for us to characterize the thermal electron number densities and the magnetic field strengths just from the observed rotation measure fluctuations alone. And not only that, quantitatively, if you can see the red dotted box over here, the conventional rotation measure analysis actually cannot distinguish between various distinct distributions of densities and magnetic field strengths, whether they're uniform, Gaussian, fractal, or log normal. And on top of that, the conventional rotation measure fluctuation analysis do not work for fractal and log normal density distributions. And if you think a little bit more carefully about this, it is actually quite a problem because fractal and log normal density structures are very common in many astrophysical scenarios like the intracluster medium and even molecular clouds. So in the last couple of minutes, I'm sure most of you are hungry already, so I'll be on time. I just wish to highlight several subtleties that we need to be careful of when we try to quantify rotation measure fluctuations correctly. So firstly, fluctuations of density and magnetic fields along the line of sight and across the sky plane can be different. So for example, what you see on the sky are two similar angles. However, the polarization angle changes along each line of sight A and B. A has two characteristic length scales and B only has one. So yet, none of these length scales through A and B correspond to the length scale that we see on the sky. So what this cartoon is trying to show us is that when we take a radio picture of the sky and derive a correlation length scale of the magnetic field, it does not necessarily translate into the correlation length scale of the magnetic field as it travels from the past to the present. Another point to note is that different astrophysical conditions give rise to different polarization fluctuations. So here's a schematic that shows various situations possible that we can have when we measure rotation measure fluctuations on the sky. So for example, in A and B, where you have a background source or not, or B and C, where you have multiple sources with various Faraday depths, or even in the simplest case, like E and F. So we only have one single source, whether it's located at a low redshift or high redshift, we still have to consider the expansion of the universe, so the radiation frequency change that happens to the light when it travels from the past to the present. So in summary, if any of you fell asleep at some point and just want to go home with one key take-home message today, it is to please keep the Stokes polarization. So we need to be very careful when we do magnetic field studies using rotation measure methods because of all the implicit assumptions that I mentioned earlier. And therefore, we would suggest to use a covariant polarized radiative transfer calculation as a more robust alternative. So if you have any questions after this, feel free to speak to me or Jennifer, or have a look at these two papers over here. So thank you.
Questions and comments, please. Down.
Very nice, Alvina.
Thank
If
you.
you could go back 2 slides to 20. So you're making, my question is, if you only had scenario B with a single length scale, is it also true that there's no particular relationship between the length scale on the projection on the sky and the correlation length in the medium?
So this is to do with the direction we're looking at, right? So the correlation length scale along the line of sight and across the sky plane can be different, which means that, for example, in B, like you mentioned, it has a longer length scale than what we see on the sky because that's the correlation between the two angles. So I would say that in some cases it's not necessarily the case, but if we get lucky, it may be the same. So it's hard to tell.
Okay, thanks.
Any other question for me? Any online comments?
Everyone is hungry.
Okay.
Oh, thank you.
Thank you, Alvina, for nice talk. So maybe we could discuss in the discussion session, but,
Sure.
but I'm particularly curious about how this kind of general stuff could be applied to FRB. So could you
Right.
comment on it?
Sure. So conventionally, people would like to use radio galaxies or quasars, things that are highly linearly polarized, as background lighthouses. So you see all these galaxies, and then we can measure the polarization and the radio emission, and use that to understand the large-scale magnetic field properties. So the magnetic field strength, the magnetic field direction. Of course, FRBs are a hot topic these days, promising candidates to be used as well because they are also polarized. We can use them on top of radio galaxies and quasars to better understand magnetic fields.
Okay. Thank you very much. If no more questions, let's thank Alvina again.
you.